Hello, everyone. So yes, as said, I'm going to show you our trip towards common sense and robotic perception. So as you might have noticed, the world was not made with robots in mind. Sorry. Okay, so as you might have noticed, well, it's not meant with robots in mind, especially in the latest years. We had this movement of like minimalistic environments. We want everything without knobs, without making any noise, without textures, without colors. And of course, this is a huge problem, especially for roboticists. So if any of you have worked with hardware, it's a pain. So of course, this causes a lot of questions, especially for robotics. First of all, spatial representation. As you might know, here it's a computer vision conference, so of course, everyone's doing point clouds, everyone has huge 3D representations. But if you have hardware, you cannot do that. It doesn't work. We have limited compute. Then, so how do I represent the world? Then what happens with dynamics? Okay, I have a static representation now, but what happens with things that move? Then further, the human in the loop. We want to do this actually, to have robots interact with actually humans. So what happens with that? And then there are much more questions there, of course. So I will tell you our storyline on how we basically have been kind of like addressing these things. So let's start with the first approach to robotic scene understanding, which is Spot Compose. So Spot Compose was a very motivated master student that decided to try out pairing computer vision with robotics. So we have at the beginning a scene reconstruction, which we have 3D instance segmentation on top, which you can see, and then we had two approaches. The first one, we have object retrieval, and the second one, we have drawer manipulation. So in the first part, we have basically the different grasps. We establish with the deep learning network the ideal grasp, and then in the second one, we actually detect where is the handle, where can we interact with, and then do an interaction. So this looks like this, actually. So you can see Oliver is asking the robot for a water bottle. And basically, you have the 3D segmentation. We, of course, need to find first where the bottle is. There you have it. We try to find the ideal grasp. And there. Now Spot is performing the act. This looks all extremely slow because basically, the robot tends to break things, and he tends to break himself. So that's why we put everything actually very slow. And you can see there. In the end, he manages to bring the water bottle. And then, basically, the question that we all had, where is my keys? Well, here in this case, Spot is searching in his drawers. Where are the keys? And he is basically doing what we all would do. We look in the drawer. Where is it? Well, there it's not. So in this case, the search is quite short. He basically, as you can see in a second, he manages to find it actually in the second drawer. So actually now we have a robot that can bring us objects and it can search for us things. But this basically brought us to some conclusions, which is, well, point clouds are way too heavy to represent the world, especially on a robot. And second, what happens with dynamic elements? But at the other side, robotics and computer vision are great tools to pair with each other. So we did the next step, which was Spotlight, which was presented at Humanoids 2 weeks ago. And so Spotlight has still the same starting point, but in this case, what we did is we have the moment 0. So we basically create from that 3D scan and the instance segmentation, we create a scene graph. That scene graph is basically our static initial assumption. And then from there, we basically, like in this case, we're trying to find light switches. So we basically find the light switch semantically. Then we do post-refinement, since the graph in the end has 3D information, but because in the end, the nodes are the instances and the edges are the distances we get from the map. But of course, we don't have an accurate position. So we do post-refinement, and then we do the affordances. In this case, the affordances mean what type of light switches is it? So a double light switch, do I push in the middle? Do I push up, down? That's what we mean here in this case. And then we can populate our scene graph, which in the beginning was metric with actually functionalities. So first of all, we bought every light switch we could get in Switzerland, and we had Spot try them out. I think it just looks very nice to see him doing all of them. And this is basically how it looks. So you can see here, we have the 3D, then we have the scene graph. It's not visually appealing to look at. That's why you will see it in a 3D point cloud. But basically here, Spot is doing the post refinement. He basically finds the light switch, clicks the button, and now he's doing what we all would do, which is, I know where the lamps are, let's check which one actually changed state. So it's basically checking, there are 2 lamps, which one turns, and now we can actually connect 2 nodes with each other, basically with the functionality, this switch turns on this lamp, which is what you would do in your memory when you enter an environment that you don't know. So here's now trying the second one. So basically what we can do now is we can pair a scene graph with 3D information and add functionalities, which is actually like creating a memory that also a human would have. So this brought us to some conclusions, which are basically most interactions can be reduced to linear and rotational motions, and the power of scene graphs. So they are nicely interferable with VLMs, and it goes beyond physical connections. So this is actually like a huge power for us. So now we added the human in the loop. So the setup is the same as in Spotlight, but we added now a human with ARIA glasses that is basically like recording and interacting with things and dynamically moving things actually around. So what you can see is like basically we first do hand object tracking, and then we do the point tracking of the object that is actually moved, and then we update the scene. So here you have Tjark. He's interacting with this nice picture frame, and he's basically moving it. But now you can see actually the node of the frame is moving while he is actually interacting with it. And we can dynamically update the scene graph by reconnecting the node to the closer ones. And so we can actually track dynamic elements now in the scene. Of course, we need to be able to see them. But you can see here that basically we have some kind of byproduct which we can learn, which is the fact, so Tjark is here hiding the plushie in the drawer. And basically, Spot can imitate the same trajectory. So he can actually, without having to do reinforcement learning or imitation learning, just imitate the same kind of action that we have from the ARIA glasses, which we get out of it. And basically, also something that I really liked is the fact when we hide things in drawers, it's not that they're gone, we just cannot see them. Well, the scene graph allows us to actually connect this, have the information that the cow, in this case, is hidden in the drawer, and this information can be accessed by the agent that is also in the scene. And then we can actually like basically go ahead, find the cow, and in this case, reunite the cow with the plush monkey that is sitting on the yellow chair. I'm going to give you a second to enjoy that part. There you go. So the conclusions, of course, here, scene graphs are for us the way to go. They are lightweight, effective data structures to understand the environment. We can easily update them with dynamics, and it offers endless opportunities to add information. We can literally store everything we want in it because it's a dictionary in the end. So can we do multi-agent? Well, yes. We added a second spot. In this case, this one had a basket. The one with the basket is called Softy. The other one is called Fluffy. And basically, you can see they are assisting each other. On one side, the one is basically checking the light while the other one is pushing it. And on the other side, basically one is getting the object out of the drawer while the other one brings it to us in the basket. So you can see that actually like underlaying all of this is a scene graph, which is shared between the human that is deciding what tasks to do and the robot that split basically the information. Who can do what? One can carry an object, the other one can pick it up. So of course they are sharing and splitting the tasks. So overall, we have now a light rate representation of the scene. We detect and track dynamic changes, we identify functional properties, and we create a shared memory between humans and operators. But 3 things are missing. Can we align cross-device experiences? Can we upscale this from a lab setting to a real environment? And is there a knowledge transfer between humans or robots? So this brings us to, we all have different viewpoints, which is Crocodile. Crocodile is a data set that we created 2 years ago, which is like 10 locations, 7 new ones plus 3 from the Lamar data set. It has temporal changes and 10 centimeters ground to accuracy. And this uplifts the entire thing to actually real world environment. So just to give you an overview, these are the most used visual localization data sets. And if you just take the ones that have multiple agents, we're left with this. And then if you just take the ones that have many locations, we're left with this. And then the 2 that we're left, one is synthetic. So we have the gap between synthetic and real. And the other one literally has an overlap of 2 agents per scene. But indeed, this is kind of like, it's also all on a brick on top of the agents, so you're not using the original kind of cameras. And then we have Lamar, which was the predecessor of Crocodile, which basically had mixed reality and handheld devices, but Crocodile adds drones and ground agents to this. There's the sequences. It's also much more than the others. So if you ever wanted to have your visual localization and SLAM pipelines running on Swiss bunkers, now it's your opportunity. So you have actually like multiple catastrophe scenarios, which we recorded. And here you can actually get a fly-through to them. One is the Sukkulentensammlung, which is a plant collection in Switzerland. And the other one is basically like a hydrology lab where they simulate water dams in small scale. So you can see the blue one is Spot. Then above, we have the handheld device. And then further above in green, it's actually the HoloLens, which is the head device. Sadly, back then, we didn't have ARIA glasses. So if not, our life would have been much easier. But you can see all of this is aligned. Everything has a ground truth with a Navis scanner. And basically, of course, we had to benchmark this. So we had to basically build from one of the devices, we built the map, and we localized the queries from the other. As you can see, each device in itself can localize well, but Spot in iOS, of course not. And this is basically because Spot first of all, one is grayscale camera and looking below. The other one is colors camera and much more above. One triggers just one image, one has multiple. So if one image doesn't localize, well, it doesn't find the match. So we decided, of course, this had many parts of the pipeline. So we decided to check which one it was. And it is, as it seems, the retrieval, which basically by assuming a perfect overlap with the ground truth, you can actually see that it improves quite a lot. But in the end, still the viewpoint difference between Spot and the handheld devices is just too big. So the viewpoint is actually still a challenge. So the conclusions are cross-device localization has unexpected challenges. Matching and retrieval are still a problem. And there are basically other issues like, well, grayscale global shutter, HoloLens and Spot cameras versus RGB rolling shutter iPhone camera. So all of these are challenges that as soon as you move to hardware, you have them. So I don't want to tell you too much about this because there is a workshop on this. So in case you want to attend to it, you can basically come and see our Crocodile in real life at 1 p.m. in room 301B. So overall, we fixed another problem, which is we can more or less align cross-device memory. But now this brings me just to my last part, which is can we upscale this and do knowledge transfer? Well, we have some challenges. Some of them you saw them. How can we make this to your home challenges? Well, perspective issues. Spot and you don't see the same. And of course, hand versus gripper. You have 5 fingers. He has 2. Well, we of course had to data record. So this is an overview of the data set. It's highly anonymized. So it's over 25 environments. We have 3D ground truth and panoramas. We have RGB depth video sequences. We have forces, touch sensors for each of the plus 235 articulated parts. So literally you have interactions now in multiple scenes. What type of interactions? Well, you have 7 different human interactions, 3 different grippers on a stick interactions, and then 1 to 2 robot interactions, because the robots were very sensible for this environment. So the viewpoints that we recorded are egocentric human perspective, of course with ARIA Gen 1. And then we have the egocentric wrist perspective, which I like to call the egocentric robot perspective, which is from the wrist, since the robot in our case doesn't have a head. And then the exocentric perspective. So what can we use this for? Imitation learning, VLAs, intent prediction, everything you can come up with, this data is going to be amazing for. So this is ongoing work, so stay tuned. And just to finish, get in touch if you want to do master's thesis, PhD, research day, just want to chat about any of the research, just feel free to let me know or talk to me in the hallway. And of course, this would have not been possible without this huge team of people. So yeah, and of course the heart of our team, which are robots. They all have also names. And yeah, thank you very much.